Hi, thank you, and thank you for the organizers for inviting me. I have been enjoying myself listening to the talks during the workshop, and so I'm here now today, and then I'm leaving, but I hope to be back in November. So I know that part of the people are staying longer, so I hope to catch up with the folks that are there that will be in November, and also, well, today. Well, I'm a physicist, and so this talk won't be so technical. But I hope you'll enjoy it, and I'll hope you stop me because as any discipline, it's full of jargon, and I don't want to use too much jargon. So I might use it without noticing it. So just stop me and interrupt me with questions at any time. I want to talk about relaxation of physical systems and some sort of an unusual relaxation of the physical systems, which we like to call anomalous. It's a little bit different from what people call when they say what they mean when they say anomalous diffusion. But here, anomalous is in a sense not your expected. It's kind of counterintuitive. And on this journey, so of studying thermal relaxations of physical systems, I was helped by my graduate students, and Saika Vera is the first graduate student that graduated with a PhD with me, and then a bunch of amazing undergraduates. So this talk, you can ask me if you like something. I can recommend literature, in particular, if you would like something nice to read, which hopefully will go across disciplines. We are currently writing a review with my co-authors Oren Raz, John Betchhofer, Antonio Lasanta, and Gianluca Tesa, and the plan is to finish it in August. So when I say to appear, I mean we have a deadline to, finish it in August. And the reason why we are writing this review, because there has been a lot of work, especially on a prime example of anomalous thermal relaxations called the Mpemba effect, not Mbappe, Mpemba. Okay, and I'll tell you what I mean by it in a second. And of course, I should acknowledge NSF for funding. So interrupt me, please, at any time. All right, so let me tell you the motivation, so the phenomenon itself. And you'll see it will be more general than this because, as always, the real system, we don't know how to describe. The real system is water. And the phenomenon, you must have heard by now, because it's been known forever. So even Aristotle writes about it. The phenomenon is sometimes called that hot water freezes faster than cold. And so the phenomenon starts with like this. Aristotle observes that if you want to freeze water quickly, you'd better put it in the sun, or somehow putting it in the sun, it might help it freeze faster. Then Francis Bacon noticed that slightly tepid water freezes more easily than utterly cold. Then René Descartes says that that in the water there are some solutes, and it's best to first let them evaporate, and then the water can freeze faster. So the hero of my story today is Erasto Bartolomeo Mpemba. Erasto Bartolomeo Mpemba in the 60s was a Tanzanian schoolboy. So something like 9th grade in America, and he was in the important business of making ice cream faster. All right, so you cannot deny the importance of making ice cream faster. His way of making ice cream was putting in an ice cube tray milk with sugar and putting it in the freezer, and so other kids were doing it as well. One day, rushing to have a freezer space, he put it with kind of lukewarm water. and observed that his froze faster, although his starting point was warm water. Then, to quantify this a little bit, together with Dennis Osborne, they made an experiment in '69 that attracted later a lot of attention, and especially in physics education. So their experiment was, yes. He didn't take into account evaporation. You have the real effect even if you correctly account for evaporation. I don't know about that. That's like, yeah. I don't know that he writes about this. There is a exchange between Descartes and Mersenne about his observation, and Descartes writes back that he did it himself, the experiments, and so now I know all of these beautiful little facts because of the writing this review, and so at least he kind of did it himself, the experiments. So, and but this guy, so Erasto Mpemba, he was in charge of game, so a wildlife manager later in life, but this was something that he measured back in '69 with Dennis Osborne with water. They took Pyrex beakers, like 100 centimeters cubed, and they made sure it's well isolated. They put it in the freezer, and they isolated it from the bottom and on the side, so all the loss was from the top, and they measured something like this. Now, I don't know how about you, but for me, when I see something like this, I am immediately I want the error bars. There were none, but the trend is evidently sort of different from what you would expect. This is the initial temperature, and this is time to start freezing. You can improve on all of this. What do you measure? What do you exactly call time to start freezing? Is it some sort of a slush of an ice and water? Where do you put your thermometer? And since some people have improved all on this, but this is evidently non-monotonic because although they have only one point here, but the whole curve should be different. The kind of, if you are cooling things slowly, the further away you start, maybe the initial gradient will be faster. Kind of the initial gradient will be proportional to the temperature difference. But otherwise, your intuition would say that if you are starting off kind of like warmer, it would take a longer time to cool down. And because you don't often see a title which has a question mark inside, and an abstract like this, I like reading it. So he says, my name is Erasto Bartolomeo Mpemba, and I'm going to tell you about my discovery, which was due to misusing a refrigerator. All of you know that it's advisable not to put hot things in a refrigerator, for somehow you shock it and it won't last long. So it's a kind of cute anecdotal story of how essentially something like a thermal quench that I will be talking about re-emerged and re-intrigued people. So what happens since then is it gets picked up mainly by physics education, and also gets picked up, and then there is a huge debate whether or not it's true. And so some people replicate it because it seems like a do-it-yourself experiment, and some don't. Then I think the Royal Society of Chemists in 2012 invites many people for competition to Mpemba is one of the judges, and Dennis Osborne. That picture is, I think, from that competition, to come up with the best explanation and to come up with the best experiment. Best explanation today, we don't know. Most of the experiments showed it. What I can tell you is that the effect in water is real, but the main culprit is very much depending on how you cool or heat, and it's still debated. What I can also tell you, and what the talk is about, it's a far more general effect, and we are all inspired by Mpemba's water experiments. You don't need water to have it. So let me tell you what is it. So for a moment, let's make a Gedanken experiment. Let's have a system prepared at a hot temperature and another system identical to it prepared at a warm temperature. And we will do two experiments. In one, we will couple the hot system with the bath, which is the coldest. And in another run, we will couple the warm system with the bath, and then we'll see what happens. So this curve here is a line, which is an isolocus of temperatures. And it happens that at thermal equilibrium, your system, instead of being described by a very complicated probability distribution function, which knows precisely the configuration, becomes much simpler and can be described, for example, by only a couple of macroscopic parameters. Typically, it's just the energy that is important. And so it's the Boltzmann distribution, just the energy of your system that's important, and the temperature. So temperature as a characteristic only exists along this line, and the line is in this highly dimensional probability distribution space. Currently, it doesn't matter whether the system is discrete or continuous. And what you do is you cool. And when you cool from here, so if you're cooling slowly, then you're always on the line or close to the line. And then at some point, your system reaches the warm start. And from then on, it cools to the bath temperature. So clearly, kind of being here, it takes longer to arrive to the temperature of the bath. That's what physicists like to call quasi-static. If I were to cool my beaker, if Mpemba were to cool his beaker this way, it would mean that he kind of like lets the environment be slightly colder than his beaker, and then the water in the beaker reaches that temperature, and then he kind of drops it a little bit, and then the beaker catches up, drops it, and the beaker catches up. And if he does this, then there is no effect. The hot start always takes longer. If, on the other hand, he does what he did, kind of isolates it well, and this is like a delta function. The system was in a step function, was in one environment, and he shoves it in a different environment, then all bets are off. Your system need not go. In fact, in general, it doesn't stay close to thermal equilibrium. So if it doesn't have to stay close to thermal equilibrium, then this is you have different routes how to reach the vicinity of the equilibrium of the bath, and that's what we call a thermal quench. So here, along these gray paths, there is no even notion of temperature. Temperature exists as an initial label. Initially, your system was in thermal equilibrium. It had a well-defined temperature, and it exists at T infinity. And then the question you want to ask, the question that we will ask is, what is the time that it takes to reach this vicinity of this equilibrium, okay? And is it possible if you started in some sense further away? Now here, for explanation purposes, temperature is perfect. You don't have to play this game with temperature, but I'm playing it with temperature right now to explain it. Sort of, I started further away because if I were to measure the probability distribution here is vastly different from the environment, more so than if I were to measure between these 2 points. Then I ask, is it possible that this is a preferential initial starting point? And the Mpemba effect we have when the underdog wins, when the system that started further away overtakes the system that's closer and cools down faster to the bath temperature. There is heat exchange with the reservoir all the time, right? Sort of, that's why you have this relaxation. So just that, so I guess, yes, of course. You could do an adiabatic process. So these lines can be, so from this point on, which route you take, it depends on what kind of a relaxation operator. So for this crowd, maybe you want to take some sort of a Markov process. Maybe you want to have this Markov process that that obeys detail balance, doesn't obey detail balance. Maybe it's your favorite Monte Carlo, like Metropolis Hastings, doesn't matter. Sort of, you have an initial point, initial sample of your system, which is well defined at this temperature, and then you just go off. Now, in heating, you can have everything that I said can work also in heating. And in fact, if you, so in fact, it's beautiful, sort of, it's by Jive, Liu, and Oren Raz, and as well as Kumar, Shetrit, and Betchhofer. The reason that I like it is that it's maybe even more surprising in the sense that, well, at least coming from, let's say, looking back at metallurgy of how you do annealing, or looking back at simulated annealing as a numerical method. So if you want to find some sort of better better minima in some landscape, you would raise the temperature allowing your system to escape some metastable state, and that would maybe allow you to find some better minima. So the fact that you can heat something up in order for it to cool down more efficiently, it does not sound as counterintuitive as the inverse, that if you want efficient heating, you might benefit from pre-cooling your system, okay? But both work, and both have been demonstrated to work even in systems that you know very well, like overdamped Langevin evolution, so just a particle diffusing in some landscape. Right, so this says the same idea, that you have some equilibrium locus, and let's say you, instead of being the space of probability distribution, it can be a space of where your observable lives, and then thermal quenches, you go off this equilibrium locus with some other protocol, and the question is who arrives faster. So observations. So I told you about water, clatrate, hydrates. Depending on the chemist you stop, they would say, oh, it's the same as water, or they would say, no, it's not water, but very similar to water, also has hydrogen bonds that have been kind of like, some people have suggested breaking of hydrogen bonds, and this being a mechanism of more efficient cooling, besides other things like inhomogeneities and convection plumes, and then granular fluids, colloids, polymers, lately quantum systems as well, magnetic alloys, and numerics. Numerics has an even larger array of systems where you can do it. You can design it you can design it in, for example, in systems that have no equipartition. So equipartition means that all excited degrees of freedom in a physical system, they each have a budget. So kBT over 2. So all excited degrees of freedom of a gas get kBT over 2. So if your gas has only rotational degrees of freedom, then it's three-dimensional translations times n, the number of molecules. This is how many degrees of freedom each has having this much. Then if you add rotations or rotations or vibrations, then you get these plateaus. So typically physicists like this kind of like specific heat, which if you normalize it correctly, it has these plateaus, one at the 3/2 kBT. And then, so this is translation only, and then this is with rotations, and then this is with vibrations. And so kind of system without equipartition would mean that, so here all of the translational degrees of freedom are excited. Here all of the rotational and translational degrees of freedom are excited. That's why it's higher up. But so without equipartition means that different degrees of freedom contribute to the budget with not equally. So somewhere here you wouldn't have, let's say, equipartition. So if you had a system like that, then it would be, it happens. This is as a function of temperature, of how fast you excite them. Right, so many different systems have it, but with water, we still don't know why it occurs. And so how to think about this effect? So then you go back to the drawing board. And in the drawing board, you have your favorite equation that describes the probability distribution of your system. Now, it can be really your favorite equation, the master equation, the Fokker-Planck equation, the Lindblad evolution, depending on the system that you're working with. And then this P can be either probability density or a probability of your system to be in a specific point, a specific time. And R is either an operator or a matrix, which tells you how you relax. So one thing is clear. The system needs to converge to the temperature of the bath. So that's why I have to have detailed balance. So detailed balance means that it's the weighted probabilities are the same of going from X to Y and from Y to X. And they're weighted by the stationary distribution. The stationary distribution is the Boltzmann distribution here. And so my system, I'll let it evolve from some point. In my case, it will be the equilibrium at the wrong temperature, not the temperature of the environment. And with time, it will descend to the equilibrium of the environment. Okay? Questions? No. After the, sorry? So, it freezes. The Mpemba curve? I think they are cooling water. I think then you would be having some, it would be from a gas to an ice. I think you can't go further. Yeah. I think so. If they ever measured that far. Yeah, I think 80 was the highest temperature that they had or something.
Just honest. Even if they reach the same temperature TB, the particles might not be in the exact same configuration. In the sense that I could have like the relaxation of all the particles. It could still occur after this TB. For instance, I could have a glass.
Exactly.
So, but you don't care about this industry. You just care about the
temperature. That's a nice question. So I think you can play this game. You can generalize it and play it between two, for example, non-equilibrium steady states. Or you can also play it in terms of the relaxation of certain observables with a glass. But then you would have some sort of how close you are to some sort of transition or what happens to the pair correlation function of some sort of correlation length in a glass. You can play it, but it's a little bit different. And in fact, people have I know that there is this Janus collaboration, which involves a bunch of people from France and Spain, and so I know Paris is one of them, and sort of there's like around 50 co-authors on a paper. They have studied the Mpemba effect in a spin glass. So spin glass is sort of you would have some sort of right. You would have some sort of a Hamiltonian, and in this Hamiltonian you would have your pairwise interaction of spin degrees of freedom. And now this thing could be instead of being something simple, it could be let's say a random matrix, and then the way the spins are connected could be these could be Ising spins, and if you connected them this way, and your interaction was antiferromagnetic, so that would mean that they want to be misaligned. So this guy would tell that guy to be up, while that guy would prefer him to be down. So you could have, you could have this kind of frustrations, right? And the system would be glassy, hard to relax. So you can do it there. So I want it to depend on the environment. But I could, right, but I have two temperatures. I have the temperature of the environment and the initial condition. I want it to depend on the environment. It's dictated by the environment. I could make it that it depends also on the initial temperature, which I usually kind of, no, there is no current temperature because your system, sorry? Oh, well, I mean, the temperature is not a very nicely defined quantity. There is a local temperature, yes. So I'm not necessarily speaking about water, but that's why I say that it depends on the details. You might have local equilibrium, or you might have a proxy for temperature. For example, systems like granular gases, they often have a proxy for temperature, which is the square root of the mean velocity. You can have, that could be your temperature as it depends on time, and then that operator could depend on it, sort of.
The initial configuration is the typical configuration at that T.
Yes.
And then the TB is the target.
Yes. In the simplest case, it does not depend on it. You could make it depend on it. You could also make it time dependent. But so I want to consider a case where there is no memory, but of course, realistically, there's always some memory, sort of. So, okay. So then, how to measure the effect? So you need some way of measuring the effect. So you need some sort of a ruler, and maybe one candidate is the Kullback-Leibler divergence. There is no best choice here. Each system dictates its choice, and often there's more than one choice. This one is nice because it has, so another candidate would be, for example, the L1 norm. This one is nice because the sigma denotes the total amount of entropy produced at time t. And then this is the total amount of entropy produced in equilibrium. So you want to minimize this difference. And then that's nice. So for example, so basically you need to compare two functions at different times. And the events that I'm talking about and want to find are events where the hot start is initially further away from the equilibrium. If you have the correct equilibrium, this is 0. And then as time goes on, the two curves invert. So this is just a schematic drawing of what I'm looking for. And I'll show you how it looks in different systems. It's good if you can write your system as an eigenvalue problem. So this R is symmetrizable, but it's not, so it has a real spectrum, but it has left and right eigenvectors, and the first eigenvalue being the equilibrium and all of the other eigenvalues being negative. And then the evolution of the probability distribution is the equilibrium that you want to arrive to, plus some corrections. And the corrections know about your initial temperature, because they are, this is just a cross product of the left eigenvector with the initial condition. The initial condition could be anything, but in my case, it's a thermal equilibrium at T. So these coefficients now will be the main carriers of the story. What happens to these coefficients? And in the case you have a gap, which is not obvious that you do, and many systems don't, between the slowest, the largest non-zero eigenvalue and the next one. So this is not necessarily always a gap, but in the case you have, you can truncate this series to the first two terms. Because all of the there is a time after which you can truncate it, and then the game is just the only thing that has memory is A2, and the whole weight of what happens, whether you have the Mpemba effect or not, is about this A2 coefficient. And how? So suppose so A2 depends on the environment and the initial condition. As a function of the initial condition, if you start with the correct temperature, there is no correction to be made. You're already at the equilibrium. If you start at a very high temperature, so the high temperature limit is a uniform distribution. At very high temperature, all of the states are equally likely. So you know that this will flatten out to a constant. And it depends continuously between the between this TB and the infinite times. So then it's a question of how is it connected? Is it connected in a monotonic way, or it's connected in a non-monotonic way? If it's connected in a non-monotonic way, that means that there will be a time, a long time, sort of when where you're only up to kind of deviation is determined by A2, at which in the long time limit, the hot starting point will be closer to equilibrium than the cold starting point, than the warm one. Okay, and this was roughly the state of the field when I heard it. There is this Mpemba condition, and the Mpemba condition due to Žive and Oren was when these coefficients are prescribed this way. So when the correction is smaller than for the hot temperature. But then I wanted to know, why should I care about it? How often does it happen? So some statistics. Does it happen in a thermodynamic limit? So maybe it happens only for small systems, and then anything experimentally relevant would be out of the question, because this board has 10 to the 23 molecules, and also when does it happen? And I'll walk you through this in this talk, bits of it at least. So I told you that the Mpemba effect you have when A2 is non-monotonic, and then together with Oren, Israel, and Ori, we thought about, well, okay, is this all it can be? Just a slightly faster correction to cooling or heating? Can we say something different? And it turned out we can. And the reason why we can is because it has to flatten out to a constant, but the constant is not sign definite. So you can have an arbitrary amount of zero crossings between the initial point, which is a zero, and the final point that's a constant. So here I drew you one curve which has a single non-trivial zero crossing, this one being trivial because it has to cross here. And at that point, that initial condition, your physical system has no overlap with the slowest mode. So if you looked at relaxation, the relaxation at that particular point is determined by the next eigenvalue, lambda 3. And the reason why, so now experimentally you might say, well, I mean, but you'll never be able to nail and tell your nail that particular temperature. That's a real number somewhere, sort of. But I don't want to nail that temperature. It's enough that I'm in its vicinity to have the benefits. There, it's determined purely by lambda 3, but around it, the projection on the slow direction on this you know, V2 eigenvector is very small. So it would mean that I somehow know close to which point the, you know, I have no projection on the zero mode, so on the slowest mode. And another thing that's very nice about it from the point of view, if you want to do some something analytical, which we wanted to do, is the fact that it's topological. In which sense? In the sense that, well, it's like a spaghetti where I hold the ends. I kind of like know that here the constant is negative and the derivative is positive. So I know I cannot unwind this zero, okay? By knowing the ends, I know that I have to have at least an odd number of zero crossings in between them. So that is powerful because then I can look at the system at temperatures which are more accessible. Often, you know, either the high temperature limit or the low temperature limit is more accessible than intermediate temperatures. So it's just easier to work with. The systems simplify greatly. And then, so this particular point here, we predicted it theoretically. And called it the strong Mpemba effect because the relaxation time jumps from lambda 2 to lambda 3. Then it was observed experimentally, and that was rewarding to have something that you predict be observed experimentally. But maybe from these three questions, let me start from the one, basically, why should we care? So I don't know how many of you have worked with or know the random energy model. Random energy model is something that physicists like. It was invented in the study by Derrida in the study of disordered systems. It's a very simple system where so what you want to study is something complicated. You want to study spins, and you want these spins to have some interactions between them, 2 spin interactions, 3 spin interactions, and often it's highly complicated to study this. So then you want something simpler, but that also has some of the qualitative features. In principle, the one feature being there is a phase transition in this system, and the simpler system is the system where you take energies out of a hat, out of a distribution. This can be a Gaussian distribution. Typically, it's a Gaussian distribution. Doesn't have to be, and that's your sample. That's a particular realization. And then you play with the temperature and you associate transitions between different energies. Kind of certain configurations are connected, and then you can hop between them. So suppose you chose a matrix like this, matrix where you had energies Ej chosen from a normal distribution and barriers Bij. So Bij is a symmetric matrix that essentially just dampens some of the transitions. So this kind of relaxation matrix obeys detailed balance and specifying different Bijs can specify a different protocol like Metropolis Hastings or something else, and then you can look at, for example, a lower bound to have the Mpemba effect. So the lower bound with the probability that the derivative here times the constants there and then times a minus sign is positive, okay? So this is easy to look at numerically, but we also managed to say something analytically. So on this busy slide, what I want you to, the only thing I want you to notice, I'll explain up to your liking however much details you want on this slide, but what I want you to see is that the probability of having this kind of occurrence, an odd number of crossings is, so probability of having the strong Mpemba effect, which is the lower bound for the whole Mpemba effect, is finite. And what's the system? The system is I took 10 energies out of a normal distribution, and I took barriers out of also normal distribution. I think the caption is incorrect. The barriers are chosen from a kind of they were all positive, so I kind of so it's a normal distribution that's centered around 0, but then just I don't have the other part. So and then all right, so and then you take a lot of realizations, a lot of different systems, a lot of different, and for the same system, you take a lot of different relaxation protocols, and you measure on which one of those, as a function of temperature, you have such occurrences. How do you measure that? You look at the ends, and then then you create a histogram, and you get these density plots. So those are the two left graphs. The right graph is something different, and something which I would love to come back and revisit with a little bit more rigor. There is only rigor in the sense of as much as physicists allow it, but which is not rigor in this room at all. But so this is an interesting one. The reason why it's interesting is it's very easy to get these points. The points are numerics. So in practice, it means you take 10 energy levels, you take your, and now you don't average over them. So there is no averaging. So physicists like to call it kind of quench disorder. The realization is the realization you've got, and you've got to kind of like deal with it. And then the barriers, you choose new and new barriers from this assembly of random matrices for the barriers. And then you plot your histogram. What is the probability to have the strong Mpemba effect? So those are the points. That's Mathematica in minutes. The orange line is more interesting. The orange line is you try to guess your second eigenvector, and so it only works for large systems. But the system that I'm showing you for isn't really large, but you try to guess. And how do you try to guess? So you say, well, I know how my first I guess your matrix is symmetrizable. So once you symmetrize, it's easier when you symmetrize it, but doesn't matter. So you have you have your first eigenvector, which is related to this equilibrium. And then you have the second eigenvector, which you would like to guess. And the second eigenvector, you start off with just an entry of Gaussian IIDs, and then you say, well, it's got to be orthogonal to the first one because there is an orthogonal basis. And then imposing just something as simple as it being orthogonal and the system being large, you can get an assembly of, it's a different assembly. In some sense, it's comparing apples and oranges, but the two assemblies, there is a region of parameters where averaging over the relaxation protocols of one assembly and the other assembly where we guess the eigenvector gives the same results. So I want to know in a closer way, as a matter of further study of how is this what we call here the isotropic assembly related to the assembly where I just choose random barriers. So I get, and then in that case, this orange line is our analytical prediction of what it should be, what the probability should be for the isotropic assembly, where we can, because we work with Gaussian IIDs, compute this quantity and give you the value of this quantity as a function of the moments of this quench disorder of purely energy statistics, which is nice. So and usually in many cases impossible. So I am looking at the time, so I'm going to cherry pick from the rest of the talk certain nice parts. So one thing that you can ask is, does it happen in a thermodynamic limit? And if you want to ask this, does it happen in a thermodynamic limit? You can look at magnets. For example, this is an antiferromagnet. Each spin on this side is connected to all of the spins there, but none of its neighbors. And that's reflected in the Hamiltonian, which only depends on the magnetizations of the two lattices. So magnetization is a difference between the up spins and the down spins on of a given subgraph, and they are in a magnetic field. And then these flips are Glauber flips. And then you can ask, what kind of an effect can I have? And for example, physicists like to draw phase diagrams. This is a phase diagrams of the temperature of the environment versus the magnetic field. And this graph for sort of is some sort of a graph which shows you where you have such effects and where you don't. Wherever you have color, you have a type of a non-monotonic behavior, a type of a Mpemba effect, different kinds of an effect. How many zeros do your overlap coefficients have? Do you have it in heating or in cooling? Is it strong or it's weak? And we can quantify all that. And, you know, then you can start to ask very interesting questions. Does this effect, the occurrence of this effect, does it have to do anything with the phase transition? Is it beneficial for the system to be in the antiferromagnetic state? Antiferromagnetic state is a state where opposite spin, where neighboring spins are face the other direction. And the paramagnetic state is they all kind of face in the same way. That happens when you raise the temperature. And this is a line of this phase transition. So this is a large system, but it's not for thermodynamic limit. You can take the continuum limit of the equation. Your probability distribution only depends on the magnetizations and the time. And this is a kind of zoomed out graph of a much larger picture where the magnetization can vary between -1 and 1, and here from -1 and 1. And the blue line here should remind you of the blue red line where is the isolocus of thermal equilibrium. So in all of these evolutions, many of the different trajectories are shown here. So say I start from this point, and then my system travels off the equilibrium line. So it's somewhere. It still has average kind of magnetizations, but they don't correspond to any equilibrium averages. So it's always given by this, but it's just not an equilibrium average. And then sort of they evolve, and as if they kind of then hit traffic. Where they hit traffic, they hit the second eigenvector, the slow direction. All trajectories hit traffic and evolve slowly except for one. You don't have to have only one such trajectory. In this system, there's one trajectory which has no projection on the slowest mode, and that's the strong Mpemba trajectory. That's the dashed red line. And so we study effects like that, where kind of this is a mean field system. It's very easy to take the thermodynamic limit. It's very, this is a, you know, partial differential equation, which you can say something about. But if you had a many body system with not a mean field, so not by mean field, I mean that one of my spins talk to every other spin. So when I say mean field, I mean, when I say mean field, I mean that a single, you know, typically it should be some interaction coefficients. Let's say it's a constant, like for me. This is not mean field if I prescribe that who is neighbor to whom. So by mean field, I mean that this guy views some average field. So then it becomes like e to the minus beta of S average squared. Mean fields are easier, but you can also do this if it's non-mean field. You take your spin system, you linearize your dynamics, and then on your manifold you have a fast approach and a slow approach, and you ask what happens there. And there is a lot of intuition I could speak about. Maybe I'll say one thing because the title of the workshop has diffusion in its name. So maybe I should say something about diffusion. So this is a Brownian particle, and it's in some, suppose, you know, it's in some potential, and then it's overdamped, meaning the inertia is not important. Now, for water, I think inertia is important, but, and then you have your particle forced, and there is some noise. The noise is white, and the diffusion knows about the temperature of the environment. You diffuse more if you if the temperature is higher. One way to look at this is to write a Fokker-Planck equation for the probability distribution of your particle being at a coordinate x at time t. And then if you want to play the same Mpemba game, you can start from the wrong stationary state where you have t, no subscript tb, and you can ask what happens to it. And so, for example, John Betchhofer and Abhinash Kumar asked this, and here you see the initial position for a hot start, so a uniform distribution, and a particle is in a double well potential. That's why the cold temperature has this bimodal peak. This is the control experiment. You start in you start at the correct temperature, you stay, you measure, and most of the particles are either in one minima or the other minima. This is a cold start. It already resembles very much the final state, but sort of it evolves to it, and this is the hot start. And then my question on this particular system would be, I'm searching for occurrences that the blue curve morphs into the final curve faster than the red one, essentially. And this is one striking a nice occurrence. So we predicted the strong Mpemba effect, where the relaxation was given by the second slowest mode, and this is precisely that. So this is the L1 norm. So these are not individual trajectories. L1 norm, kind of the difference between the probability distribution at a specific time initially and at final times. And you see that there is a dip in the relaxation time, and that's the strong Mpemba effect that we predicted. And so the shape of the potential is important, the geometry is important, and with my student, we connected it to mean first passage time and how it's related to all of these things, and found corrections, and you know, explain some of the intuition behind the Betchhofer's and Kumar's experiment. And yeah, as you can see, I can go on forever, but I want to allow both your questions, and I want to allow Bernard up. Well, I guess I keep creating new slides. That's not good for you. I want to allow, yeah. Thank you. Or comments on how I can make this more exciting, or I don't know.
Just argument controlling. So I have the TH, or I have strong and Pember effect. So whether A2 is the same for TH and TB, what determines the size TH minus TB? Like, is there ever a case, or what rules out the case being TH being very close to TB? Will I ever see the strong and Pember effect? I think it's hard. I think it's if it's very close, then you don't see it. Then it's like this Newton law of cooling. But if it's not, sort of, so this A2 as a function of temperature, so you're making it. I mean, it's possible. You're making it want to kind of like curve very close to where it already did. It depends on other parameters of your system. I've seen it happen. You can continuously change and deform this A2, but I guess I would need to specify a system. Maybe we are talking about some potential, and so it has some. So maybe that's some polynomial, and now you're asking as a function of the coefficients of that polynomial, what is the chance that you're asking what is the chance that I'm gonna have so the condition for the strong Mpemba effect in the case of two well potential is this thing. Roughly being the same, and kind of for let's say the left well, for this domain. You know what it means? It means that all of the guys. I'll just take half a minute, and if it's not half a minute, then I'll stop. It means that where you have the strong Mpemba effect, it's when the area of this red rectangle, the hot start, is the same as the area under this curve. So it means so in the case where you have two well-separated wells, it means that all of the guys that were supposed to be in this well are already there. The switching is anywhere rare. They just need to reconfigure, and instead of being spread everywhere or around this left well, they need to congregate close to the minimum. I should stop. I am happy to talk more afterwards. Thanks.